Hello everyone. Today we're looking at the scientific definition of work. Work is the transfer or transformation of energy in a system. So transfer would mean if energy is coming in or going out of our system, and transformation would just mean if it's changing from one form of energy to another within a system. Work occurs when a force acts on a moving object, so there needs to be a displacement, and that force needs to be either with the displacement or against the displacement, causing or opposing the motion of the object. Okay, some examples of work. When two students push an out-of-gas car to move it towards a gas pump. What you're seeing in each of these examples on the screen is the requirement that we have is there has to be a force, there has to be a displacement, so the object has to be moving, and we have to have at least a component of the force that is in the same direction or opposite direction of the displacement. Okay, so some part of the force has to be collinear with the displacement. Some examples where work is not occurring because one of those requirements isn't upheld. For example, a teacher applies a force to a wall, but the wall doesn't move. So if we're not seeing a displacement, then that force is not doing work. It's not causing a transformation or transfer of energy. Also, if we see a force that has no component parallel or anti-parallel to the displacement, then that force is not doing any work. Okay, straight from the equation sheet for work, it says force times displacement times the cosine of theta. It also says on our equation sheet, do force parallel times displacement. That is, we only want to look at the component of the force that's in the same line as the displacement. Okay, so for example, if the angle between the force and the displacement is 0, we would call that positive work. This is a force that's in the same direction as the displacement, so it's in the same direction as the velocity. We know for accelerations and net forces that are in the same direction as the velocity, the object speeds up. So we would consider this to be an increase in energy. When the force is against the displacement, or the angle is 180 degrees, we call that negative work, because this is a force that's causing the object to slow down. And if you put 180 degrees into the cosine of theta, you get -1. So we're seeing negative work being done there. Another example here, when the angle is somewhere between 0 and 90 degrees, so for example 45, this force is not perfectly lined up with the displacement. So we would say only a component of this force is doing work. There's also a component of this force that is perpendicular to the displacement. So I would break this force into components. One component perpendicular to the displacement and one component parallel. And only that parallel component is doing work. And in this case, I would call that positive work, because that parallel component is with the displacement in the same direction as the velocity and the displacement, making the object speed up. And our last example here, when the force is perpendicular to the displacement, when the angle is 90 degrees, there is no work being done by that force. Again, if you put 90 degrees into the cosine of theta, you get 0. And by our definition, the requirement is the force has to have a component in line with the displacement. If not, that force is not doing any work. Okay, we're also looking at kinetic energy, the energy that an object has due to its motion. So the faster something is moving, the more kinetic energy it has. It doesn't matter what direction the object is traveling in, doesn't matter if the object is speeding up or slowing down. All that matters is the object moving? Then yes, it has kinetic energy. It's the energy an object has due to its motion. The equation, pretty basic, 1/2 mv squared. So the kinetic energy of an object is due to its mass and its speed, and then we're going to square that. So 1/2 mv squared. We can take a look at the units that we get when we just by analyzing this equation. So we get a kilogram from mass, and from speed we get a meter per second, but the equation tells us to go ahead and square that. So what we end up with is a kilogram meter squared per second squared. And that is a mouthful. We don't have to say that every time. So when we have a longer unit like this, we typically just name it after a scientist. And in this case, we're going to call that a joule. So the unit that we use for energy is a joule. It's also saying here that a joule is equivalent to a Newton meter. And I could take this kilogram meter squared per second squared, and I could pull out the Newton, or a kilogram meter per second squared, and I'm left with that meter on the other side. And that's an important equivalency, that a joule and a Newton meter are the same, Because when I look at the equation for work, I would get from force, I would get a Newton, and from displacement, I would get a meter. So what we're seeing here is there's an equivalency between the unit of work, Newton meter, and the unit of energy, or in this particular case, kinetic energy, which is joules. And that equivalency leads us probably to the most important thing that we're going to look at in AP Physics 1, and that is the work-kinetic energy theorem. It says that the net work done on an object is equal to the change in kinetic energy of that object. So we can make sense of that with what we already learned in kinematics and dynamics. For example, if the force is causing an acceleration in the same direction as the displacement, back in kinematics, we said that means the object speeds up. And if the object speeds up, that means that it's increasing its kinetic energy. And that is positive work being done that added energy to the system. If the net force is causing an acceleration that's against the displacement, that's going to cause the object to slow down, which means the kinetic energy is decreasing, and we're looking at negative work being done because energy is leaving the system. This might be something like friction that's doing negative work to make the object slow down. So that is what we see most often, the work-kinetic energy theorem. Just keep in mind that work is change in energy, transformation of energy, transfer of energy. The net work done on an object is going to always equal the change in kinetic energy. If the net work is positive, then the kinetic energy goes up. If the net work is negative, kinetic energy goes down. This below is directly from the Physics 1 equation sheet. Just wanted to add here that, they write it a little bit more formally. They say the change in kinetic energy is equal to the sum of all the work that's being done. So they have that Greek letter sigma, and that just means that work is additive. So if a force comes along and it does work on an object and it changes the kinetic energy, and then another force comes along and also does work, we can just continue to add those works together to get the total change in kinetic energy. So that's the only reason why they have that sum there. What I prefer to look at is kind of the cleaner version right here, that work is just equal to change in kinetic energy. If I get multiple forces doing multiple work, then I'll continue to add them together. Okay, the last thing we might have to do is rearrange the kinetic energy equation, right? Kinetic energy is 1/2 mv squared. We might have to rearrange that to find an unknown mass. So to get rid of this 1/2, I don't like having that fraction. So I'm going to multiply by 2 instead of dividing by 1/2. So I think that makes a lot more sense, and it's easier to put into a calculator. So I'll multiply by 2 and then divide by v squared to get mass by itself. So that's not too bad. The last one, if I wanted to get the speed, I would again multiply by 2 to move it to the other side and then divide by mass, but that would give me v squared, and I don't want v squared, I just want v by itself. So the last thing I would do is take the square root of both sides. So we end up with the square root of 2 times the kinetic energy divided by the mass. Okay, so that is something you might be expected to do on the exam. That's it for today. So that is the end of kinetic energy and work-kinetic energy theorem. What we'll do next week is potential energy and also conservation of mechanical energy. So that's it. Thanks for watching.